A team of cosmologists is staring at a number on a screen, and nobody in the room is saying anything. They ran the math 3 times. Each time it comes back the same way, and each time it gets harder to explain away. The calculation says something that sounds impossible. If you take everything we can see, every galaxy, every star, every cloud of gas across the observable universe, and you divide it by the volume of space it fills, the density crosses a line it shouldn't be able to cross. That line is the threshold for an event horizon. Cross it, and light stops leaving, which raises a question nobody in that room wants to say out loud first. Are we already on the wrong side of it? Before we get to that number, we need to go back to the moment humanity first realized space itself could trap light. 1783. A quiet English village named Thornhill. A clergyman named John Michell sits down and does something almost nobody else in his century bothers to try. He takes Newton's laws of gravity and light seriously enough to push them to their breaking point. Light, Michell reasons, should behave like anything else thrown upward. Throw a rock fast enough and it escapes Earth's gravity. Throw it too slow and it falls back. So what happens if a star is so dense, so packed with mass, that even light doesn't throw fast enough to get away? He calculates it. A star roughly 500 times the radius of our Sun, with the Sun's density, would trap its own light completely. He calls it a dark star. It would be invisible, detectable only by the gravity it exerts on anything nearby. Michell's dark stars would sit forgotten for over a century, until a soldier in a war zone solved an equation Einstein said was unsolvable. 1915. Karl Schwarzschild is a German astrophysicist serving on the Russian front during World War I, calculating artillery trajectories between shifts in the trenches. That same autumn, Einstein publishes his general theory of relativity, a set of field equations so complex that even Einstein doubted anyone would find an exact solution. Schwarzschild finds one anyway, in a matter of weeks, from inside a war zone. He mails his solution to Einstein, who is reportedly stunned that anyone solved it that fast, let alone under those conditions. Buried in that solution is a specific radius. Compress any mass down inside that radius, and Schwarzschild's math describes a boundary where space-time itself curves back on light. We call it the event horizon today. He was describing, with pure mathematics, exactly the kind of object Michell had guessed at a century earlier. Schwarzschild's solution worked perfectly, except for a place inside it where the equations simply broke. Right at the center of Schwarzschild's solution sits a point with zero size and infinite density. Squeeze all the mass of a collapsed star into a single dot with no dimensions at all, and the math stops behaving. Gravity doesn't just get strong there, it becomes undefined. Physicists call this a singularity, and it's not a small glitch you can round away. Every equation that describes how matter and energy behave simply hits a wall and gives no answer. Einstein himself hated the idea and hoped it was a flaw in the theory, not a feature of reality. If a singularity really exists, it means somewhere in the universe there's a place where the laws of physics don't apply. For decades, physicists tried to prove this singularity was just a mathematical mistake and kept failing. In 1930, a 19-year-old named Subrahmanyan Chandrasekhar boarded a ship from India to England and passed the long voyage working through the physics of dying stars. He calculated that any collapsing star with a mass above about 1.4 times the Sun's could not stop collapsing. No known force could hold it up. That number now bears his name, the Chandrasekhar limit. Cross it, and a star doesn't settle into a quiet white dwarf. It keeps falling inward, potentially all the way to Schwarzschild's forbidden point. He presented the result in 1935 to the Royal Astronomical Society, only to watch his own mentor, Sir Arthur Eddington, stand up and publicly mock the idea as absurd. Eddington was the most famous astrophysicist alive, and the room sided with him. Chandrasekhar's career in Britain never recovered from that afternoon. He left for the United States and kept working in something close to exile from the field he'd tried to advance. It would take nearly 50 years and a Nobel Prize before the world admitted he'd been right all along. By the 1960s, the object at the end of a dying star's collapse still didn't have a proper name. Scientists called it a gravitationally completely collapsed object, which is exactly as clumsy as it sounds. Nobody outside the field could picture what that meant. In 1967, physicist John Wheeler was giving a lecture in New York, searching for something shorter. Someone in the audience reportedly suggested 2 words, and Wheeler ran with them: black hole. It described everything at once. Light couldn't escape it, so it was black. And matter fell into it and simply vanished, so it was a hole. The name spread through science and pop culture almost overnight, turning an obscure mathematical oddity into something people could picture and fear. The name caught on instantly, but some physicists worried it made something monstrous sound almost friendly. That friendliness problem ran into a bigger one. How do you find something defined by the fact that it gives off no light at all? You can't point a telescope at pure darkness and expect to see anything. Every other object in the sky announces itself. A black hole, by its very nature, refuses to. So astronomers flipped the question. Instead of looking for the black hole itself, they'd look for what it does to its neighbors. Gas and dust falling towards something with that much gravity should heat up violently on the way in, screaming out X-rays before it crossed the point of no return. That meant the search wasn't for a shadow. It was for a very specific kind of scream, a bright X-ray source with no visible object behind it, something bending space without ever showing its face. In the early 1970s, a source of X-rays in the constellation Cygnus would give them their first real target. In 1971, satellites picked up Cygnus X1, a fierce X-ray source about 6,000 light-years away. It sat next to a blue supergiant star, and the two seemed locked in orbit, the star's outer layers visibly being dragged towards something unseen. The math suggested that unseen companion weighed something like 15 times the mass of the Sun, packed into a region barely 300 kilometers across. No star could survive compressed like that. It could only be one thing, or so most physicists suspected. Stephen Hawking wasn't ready to bet his reputation on it. In 1974, he wagered Kip Thorne a subscription to Penthouse against 4 years of private eye that Cygnus X1 would turn out to be nothing. Hawking would eventually concede, but not before the discovery reframed what stellar mass black holes could even be. Cygnus X1 gave astronomers a template. A dead star collapses under its own weight, and if there's enough mass left over, gravity wins completely. These stellar mass black holes topped out, it seemed, somewhere in the tens of suns, a tidy, if terrifying, category. But by the 1970s and 80s, radio astronomers pointing their dishes at the center of the Milky Way kept finding something strange. A compact, powerful source of radio waves sat right at the galactic core, and it wasn't behaving like any stellar remnant they'd catalogued. Whatever was sitting there wasn't answering to the same rules as a collapsed star. The numbers, once anyone dared calculate them, didn't just push past the stellar mass category. What they found at the center of our own galaxy would dwarf Cygnus X1 by a factor of millions. In 1974, 2 radio astronomers pointed their instruments at the exact center of the Milky Way and found something they couldn't explain. It was a compact source of radio waves, barely bigger than our solar system, blazing away 26,000 light-years from Earth. They named it Sagittarius A star. Nothing about it made sense for its size. Stars don't pack that much energy into that smaller space, and neither does anything else astronomers had catalogued before. Whatever was sitting there was either something new or something predicted decades earlier that nobody had actually confirmed. Proving what Sagittarius A really was would take almost 30 years of watching stars dance around empty space. 2 teams took up the challenge, one led by Reinhard Genzel in Germany, the other by Andrea Ghez in the United States. Starting in the early 1990s, they aimed the largest telescopes on Earth at the galactic center and began tracking individual stars year after year as they looped around that invisible point. One star, called S2, became the key. It swung around the galactic center on an orbit so tight it completed a full loop in just over 16 years, reaching speeds of nearly 3% the speed of light at closest approach. The work took patience most fields never demand. 2 decades of images, stacked and compared, chasing a handful of pinpricks of light. In 2020, Genzel and Ghez shared the Nobel Prize in Physics for it. Their tracking revealed a mass so concentrated in so small a volume that nothing but a black hole could explain it. When the orbits were finally run through the math, the number that came out was staggering. About 4.3 million times the mass of our Sun, not spread across a galaxy, not spread across a star cluster, packed into a region smaller than the distance from the Sun to Pluto. Picture every star within a few hundred light-years of Earth, all of them combined, crushed down into a volume you could cross in a matter of hours at light speed. That's the density Genzel and Gez's data demanded, and it left no other candidate standing. Sagittarius A wasn't just a curiosity anymore. It was proof that our own galaxy carried a monster at its heart. And yet, on the cosmic scale of black holes, 4 million suns would turn out to be almost modest. Because here's what astronomers started to notice once they went looking. Sagittarius A wasn't a fluke. Nearly every large galaxy seemed to have something similar buried at its core, a dark mass pulling stars into tight, fast orbits. But the masses varied wildly. Some galactic cores held black holes only a few 100,000 suns heavy, barely bigger than ours. Others held monsters 1,000 times more massive than Sagittarius A, sitting quietly in galaxies that looked, from the outside, unremarkable. That kind of range raised an uncomfortable question. If a 1,000-fold difference was possible, what set the ceiling? Nobody had an answer yet, because nobody had actually seen one of these things up close. One galaxy in particular would force astronomers to redraw the upper limits of how big these objects could get. That galaxy was M87, a giant elliptical sitting 55 million light-years away in the Virgo cluster. In April 2019, it became the subject of an announcement that had been 8 years in the making. The Event Horizon Telescope wasn't one instrument. It was 8 radio observatories scattered across the planet, from Hawaii to the South Pole to the Spanish Sierra Nevada, synchronized down to the nanosecond using atomic clocks, all pointed at the same patch of sky at once. Together they formed a virtual telescope roughly the size of Earth itself. Over 200 researchers spent 2 years processing the data, cross-checking 4 independent imaging teams against each other, so no single group's assumptions could bias the result. The ring of light they captured belonged to an object whose mass would make Sagittarius A look like a rounding error. The number that came back was 6.5 billion solar masses, not million, billion. That's roughly 1,500 times heavier than the black hole sitting at the center of our own galaxy. Oddly enough, that extreme size is exactly what made M87 photographable in the first place. Event horizon size scales directly with mass, so a black hole 1,500 times heavier has an event horizon 1,500 times wider. Sagittarius A is closer to Earth, but it's small, and its horizon shifts shape in minutes, blurring long exposures. M87's horizon is so vast that light takes days to orbit it, holding still long enough for the array to actually resolve the shadow. M87 held the imaging record, but it was nowhere near the largest black hole astronomers had already found on paper. Direct imaging only works when a black hole is close enough and its horizon big enough to hold still for days. Almost nothing qualifies. For everything else, astronomers had to fall back on a cruder tool, watching how hard something pulls. then working backward to figure out what could possibly pull that hard. That backward math kept turning up numbers that didn't make sense at first. 10 billion solar masses, 20 billion. Numbers so far past the supermassive black holes at the center of galaxies like our own that scientists needed a new word just to file them under. They called them ultramassive, a category built for objects with no confirmed photograph, known only through the light bent and starved by their gravity. Somewhere out past the familiar galaxies, astronomers found objects so large the term supermassive stopped being adequate. The name is unremarkable. TON 618 sounds like a parking garage, not the site of one of the most extreme objects in the observable universe. It sits roughly 10.4 billion light-years away, and by most estimates carries somewhere around 66 billion solar masses. For comparison, the black hole at the center of the Milky Way holds about 4 million suns. TON 618 outweighs it by a factor of roughly 16,000. Its accretion disk alone, the swirling disk of superheated gas falling in, spans a region wider than our entire solar system many times over, glowing bright enough to be classified as a quasar, visible across most of the universe. No telescope has ever resolved its shadow. No image exists, and likely none ever will. Measuring an object this size meant inventing new ways to weigh something no human could ever visit. You can't put a black hole on a scale, so astronomers built two workarounds. The first, reverberation mapping, tracks how light from the black hole's accretion disk flickers, then measures the time delay before that flicker echoes off surrounding gas clouds. That delay, converted through the speed of light, gives a distance, and distance combined with the gas's motion gives mass. The second method watches stars or gas clouds orbiting nearby, clocking their velocity the way you'd clock a planet swinging around a sun. Faster orbits mean stronger gravity, and stronger gravity means more mass crammed into the center. Neither method requires seeing the black hole itself, only watching what it does to everything nearby. Run those numbers on TON 618, and the answer comes back at tens of billions of solar masses, a figure that's held up under repeated scrutiny. But mass alone wasn't the strange part. It was what happened when astronomers compared mass to size. Here's the part that breaks most people's intuition on the first try. A black hole's density isn't fixed. It depends on mass in a way that runs backwards from what you'd expect. Cram a few suns worth of matter into a black hole and you get something absurdly dense, way past anything a lab could ever produce. But scale the mass up, way up, and the required density actually drops. The event horizon grows faster than the mass packed inside it, so a big enough black hole could have an average density lower than water, lower than air, low enough to seem almost gentle by comparison. That single, strange fact, that bigger can mean thinner, was about to collide with the size of the observable universe itself. Somewhere in the back half of the 20th century, a physicist ran that density logic one step further, mostly for fun. If mass and size together could push a black hole's density down towards something ordinary, what happens if you scale it all the way up to everything? What if you took the entire observable universe, all of its mass, all of its reach, and asked whether it happened to sit at that same threshold? Nobody expected a real answer. It read like a bar napkin joke, the kind of question you raise to make a point about scale, not one you take seriously enough to actually calculate. It was meant as a thought experiment until someone actually did the math. The tool for that math is almost embarrassingly simple. It's called the Schwarzschild radius, and it just asks, for a given mass, how small would it need to be packed to trap light itself? The formula takes an object's mass, multiplies it by the gravitational constant, and divides by the speed of light squared. Feed in the mass of a star, and you get a horizon a few km wide. Feed in a supermassive black hole like TON 618, and that radius stretches to the size of a solar system. So physicists asked the obvious next question. What radius do you get if you feed in the estimated mass of the entire observable universe, every star, every galaxy, every scrap of dark matter astronomers could account for? What came out of that calculation is the reason this video exists. In the late 1970s, a handful of physicists ran that calculation seriously for the first time. Take the total mass energy of the observable universe, spread it across the radius astronomers had measured, and check it against the Schwarzschild formula, the same one that defines the event horizon of any black hole. The math is simple enough for an undergrad to do on paper. Mass in, radius out, compare it to what you actually observe. It's the kind of calculation you'd expect to produce a wildly wrong answer, off by a few orders of magnitude in either direction. It didn't. The Schwarzschild radius that came out of the universe's total mass landed within the same order of magnitude as the radius of the observable universe itself, roughly 13.8 billion light-years. The number was so close to the threshold that other physicists immediately started looking for reasons it had to be wrong. The first objection came fast. Schwarzschild's original solution describes a single mass sitting in otherwise empty, static space, a star or a black hole with nothing else around it. The universe is not that. It's filled edge to edge with matter, and it's expanding, which the original equations never accounted for. Critics pointed out that plugging cosmological numbers into a formula built for an isolated object might just be a coincidence of units, not a real physical result. General relativity has other tools built for an expanding, matter-filled cosmos, and those give different answers. There was a second problem, and it was worse. A Schwarzschild radius assumes something with a definite edge, a sphere of a certain size containing a certain mass. Nobody has ever found the edge of the universe. But dismissing the idea meant answering a much harder question. What actually defines a boundary in an expanding universe? Every direction astronomers point a telescope, galaxies thin out into the same faint, ancient light, the cosmic microwave background, sitting at roughly the same distance, no matter which way they look. There's no wall, no edge, no special point you could call the middle. That's not a gap in our instruments. It's a working assumption baked into modern cosmology, called the cosmological principle. On the largest scales, the universe looks roughly the same everywhere, in every direction, from any vantage point you'd choose. Which makes the black hole comparison awkward. A black hole's mass sits inside a fixed radius with empty space beyond it. If the universe has no outside, no edge to mark where its mass stops, what exactly would you even be measuring the radius of? Yet even without an edge, there was one boundary cosmologists could actually measure. Every telescope on Earth is a time machine, and there's a hard limit to how far back it can see. Light from the earliest moments of the universe has been traveling for about 13.8 billion years, and that's as far as our view goes. Beyond that distance, there hasn't been enough time since the Big Bang for any light to reach us at all. Cosmologists call this boundary the cosmic horizon, and it's not a wall or a physical structure. It's simply the edge of what's visible, the outer limit of the observable universe centered on us. Past it, space almost certainly keeps going, but we have no way to see it, measure it, or know what's there. Here's where it gets strange. When you write down the physics of that horizon, distance, causality, the point past which nothing can reach us, the equations look remarkably familiar. That horizon behaves, mathematically, more like the edge of a black hole than most people are comfortable admitting. To understand why, you have to go back to a number cosmologists call critical density. It's the exact amount of mass and energy packed into space that would make the universe's geometry perfectly balanced, neither curving back on itself nor flying apart into nothingness forever. Too much density and gravity wins. The universe stops expanding, reverses, and collapses back down, the same basic physics that crushes a dying star into a black hole in the first place. Too little density, and expansion runs away completely, stretching everything into a cold, empty scatter of particles. That threshold sits at roughly 5 hydrogen atoms per cubic meter, an almost unimaginably thin soup spread across all of space. It's the same kind of knife-edge balance that defines the boundary of a collapsed star. When cosmologists actually measured our universe's density against that threshold, the result was almost eerie. In the early 1990s, the COBE satellite took the first real measurements of the cosmic microwave background, the leftover heat from the Big Bang. Later missions, WMAP in the 2000s and Planck in the 2010s, refined those measurements with far greater precision, mapping tiny temperature variations across the entire sky. From that data, cosmologists could calculate the actual geometry of the universe, whether space itself curves like a sphere, saddles outward like a Pringle, or lies flat. The answer came back flat, and not approximately flat. Planck's data pinned the universe's density within about 0.4% of that critical value. Out of every possible ratio the universe could have landed on, it sits almost exactly on the line separating eternal expansion from total collapse. Flat isn't just a geometric curiosity, it's the exact condition a universe would need to sit right at a horizon's edge. So why would that be? A universe with even slightly more matter than critical density would have collapsed back on itself long before stars, planets, or anyone to ask the question ever formed. A universe with slightly less would have expanded so fast that matter never clumped into galaxies at all. The odds of landing this close to the line, by chance, are absurd. Run the math back to the first fraction of a second after the Big Bang, and the density had to be tuned to something like 1 part in 1060. Nudge that number even a hair in either direction, and nothing we know would exist. That's not a small coincidence. That's the kind of number that makes physicists deeply uncomfortable, because nature usually doesn't hand you fine-tuning for free. Physicists had one explanation for this improbable fine-tuning, and it would only deepen the mystery. The answer, for most of the field, is inflation. In the first fraction of a second, roughly 10⁻36 seconds after the Big Bang, the theory holds that space itself expanded by a factor of at least 10^26, faster than the speed of light, in less time than it takes a photon to cross an atom. That kind of expansion stretches out any curvature almost to nothing, the same way blowing up a balloon to the size of a planet would make its surface look flat to someone standing on it. A universe riddled with warps and wrinkles gets smoothed into something that looks, to instruments like Planck, indistinguishable from flat. Inflation solves the puzzle, and it does it elegantly. It's backed by decades of work, and it fits the data we have. But not everyone accepts inflation as the full story. Some think the flatness itself is a clue about what we're inside of. That alternative starts somewhere you wouldn't expect, the math of a black hole. When a massive star collapses, general relativity says the material inside the event horizon keeps falling, crushed toward a singularity. But some physicists looked at those same equations and noticed something strange happen at the horizon itself. The math describing spacetime just inside a black hole's boundary looks almost identical to the math describing an expanding universe. Not similar in a loose, poetic way, structurally the same equations, the same solutions, just with certain terms flipped. That resemblance has a name: Schwarzschild cosmology, or black hole cosmology. The idea is that our universe could be the interior of a black hole, one that formed inside some larger, parent universe we'll never see. What looks like the Big Bang from in here could look like a collapsing star from out there. This wasn't internet speculation. It came from physicists with real credentials, willing to stake their reputations on it. The first real math behind this came in 1972, from a physicist named Raj Pathria. He found that if you took the equations of general relativity and pushed them to their logical extreme, a universe born from a black hole wasn't just possible, it was a natural consequence of the geometry. Around the same time, mathematician I.J. Good, the same man who'd once worked alongside Alan Turing at Bletchley Park, arrived at a strikingly similar conclusion on his own. Neither man was fringe. Both were working within the accepted framework of physics, not outside it. But the math had a problem. There was no way to test it, no observation that could confirm or kill the idea. So it sat in journals, cited occasionally, believed by almost no one. Their papers were largely ignored for decades, until a black hole information puzzle brought the idea roaring back. Here's what nobody tells you when they first explain black holes. Everything interesting about them, the paradoxes, the unanswered questions, the stuff that keeps physicists up at night, doesn't happen at the singularity. It happens at the boundary. That thin, invisible membrane wrapped around every black hole turns out to be where reality gets strange. Information seems to vanish there. Space and time seem to trade places there. And it's that same boundary that may end up telling us whether our own universe has one too. We're not ready to open that door yet, but keep it in the back of your mind as the physics gets stranger from here. Whatever the answer turns out to be, it won't come from the center of a black hole, it'll come from its edge. In the 1990s, physicist Lee Smolin looked at the black hole universe idea and asked a different question. Not just could a black hole spawn a universe, but what if that process behaved like evolution? His theory, cosmological natural selection, proposed that every black hole collapses into a new universe, and each new universe inherits the physical constants of its parent, but with tiny random mutations. Universes that happen to produce more black holes make more offspring. Over countless generations, Smolin argued, the multiverse would be dominated by universes fine-tuned to build black holes efficiently, which happens to require conditions strikingly close to the ones we observe in our own. It was a way to explain fine-tuning without invoking chance or design, just selection, playing out on a cosmic scale. It was an elegant idea, and it was about to run straight into a wall of criticism from Smolin's own peers. The problem was simple. Cosmological natural selection made a bold claim, but it offered almost no way to check it. You can't observe a black hole birthing a new universe. You can't watch reproduction happen across a multiverse we have no access to. Critics pointed out that the theory could be tweaked to fit almost any outcome, which is a death sentence for a scientific idea. If you can't design an experiment that could prove it wrong, some argued, you're doing philosophy, not physics. Even physicists sympathetic to Smolin worried he'd built a beautiful story with no way to test its own foundations. Smolin pushed back, insisting his model did make one falsifiable prediction, that no small tweak to the physical constants should make black holes easier to form than they are now. That was something, but it wasn't much to build an entire cosmology on. But untestable or not, one prediction from black hole universe models was about to be checked against real data. In 2010, physicist Nikodem Poplarski took a different route into the same idea. He turned to Einstein-Cartan gravity, a lesser-known extension of general relativity that adds a property called torsion, a kind of twist baked into the geometry of space-time itself. In standard general relativity, a collapsing star crushes down into a singularity, a point of infinite density where the equations simply break. Torsion changes that ending. As matter collapses, the twisting force grows enormous at extremely high densities, strong enough to halt the collapse before it reaches infinity and violently repel it outward instead. Poplarski described it as a bounce. The collapsing matter doesn't vanish into a singularity. It rebounds into a new, rapidly expanding region of space-time, sealed off behind the black hole's event horizon. From the inside, that bounce would look exactly like a Big Bang. Poplarski didn't just propose the idea, he suggested a way we might actually be able to test it. Here's the logic. Black holes form from collapsing stars, and stars almost always spin. If a black hole's collapse bounces into a new universe, that new universe should inherit some of the parent star's rotation, like a whirlpool spinning off inside a bigger current. That means our universe, if it was born this way, might still be rotating on some axis left over from its birth, And that rotation should leave fingerprints. Galaxies scattered across the sky shouldn't have their spin axes pointed in completely random directions. There should be a subtle preference, a faint alignment, tracing back to the axis of that original bounce. It was a strange, almost dizzying prediction that the orientation of galaxies billions of light-years apart could be quietly linked by an event before the birth of space-time as we know it. And unlike most multiverse ideas, this one didn't require access to another universe to check. It just required a very large, very careful survey of galaxies. Someone did check, and the results split the astronomical community right down the middle. The astronomer who took up the challenge was Leor Shamir, and his method was almost brutally simple. Feed a computer hundreds of thousands of galaxy images, let an algorithm sort each one by whether it spins clockwise or counterclockwise from our vantage point, and count. In one early pass, he ran the numbers on over 126,000 spiral galaxies from the Sloan Digital Sky Survey. Later work pulled in data from the Kilo Degree Survey and eventually more than 1 million galaxies from the DESI Legacy Survey, splitting the sky into hemispheres and comparing one half against the other. If the universe plays fair, a coin flip is a coin flip. Half the galaxies should spin one way, half the other, no matter which patch of sky you're staring into. That's not quite what the numbers showed. The asymmetry was small, but if real, it shouldn't exist at all in a universe with no preferred direction. Here's what the excess actually looked like. In the SDSS dataset, the skew toward one spin direction over the other showed up with odds of roughly 1 in 170,000 that it was just chance. Not overwhelming, but not nothing either. And it wasn't random noise scattered across the sky. In the DESI Legacy Survey, counterclockwise galaxies turned up more often in the northern hemisphere, clockwise ones more often in the south. Like the whole sky had a faint but consistent grain to it. That's the part that matters. The cosmological principle, the bedrock assumption behind essentially all of modern cosmology, says the universe looks the same in every direction on large enough scales. No favored axis, no special orientation, nothing that would let you point and say, that way is different. A few percent more spin one way isn't a rounding error you can wave off. If confirmed, this wasn't a small correction. It was a crack in one of cosmology's foundational assumptions. Naturally, the rest of the field didn't just take the result and run with it. Critics pointed first at the pipeline itself. An algorithm trained to spot spin direction can quietly pick up on other features, like image orientation or brightness gradients, and mistake them for chirality. Others flagged which galaxies got included in the first place. If the selection process rejects ambiguous spirals unevenly, a handedness bias can creep in before the counting even starts, and some reanalyses using different feature sets found the asymmetry shrink towards zero. Shamir pushed back with a specific counterargument. A bias baked into the algorithm should behave the same way everywhere on the sky. The fact that the skew flips direction between hemispheres is harder to explain as a simple coding error. Neither side has landed a knockout blow. The debate is still unresolved today, but it reopened a question nobody expected to matter this much. Does our universe rotate at all? In 1949, a logician named Kurt Gödel handed Albert Einstein a birthday present that broke physics in the most polite way possible. He'd found an exact solution to Einstein's own field equations, a universe filled with rotating matter and nothing else. No expansion, no Big Bang, just a slow cosmic spin. But the real shock was what that spin allowed. In Gödel's universe, you could take a long enough trip and return before you left. Closed loops through space-time itself, time travel, sitting right there in the math. Gödel never claimed our universe worked this way. He wasn't even trying to describe reality, just testing what Einstein's equations permitted. Gödel's universe was never meant to describe reality, but its math would echo strangely in the black hole universe debate decades later. Here's where that old thought experiment stops being a curiosity. If a black hole collapses and births a new universe on the other side, that new universe doesn't start from nothing. It inherits the physical properties of the star that made it, including angular momentum. Spin doesn't just vanish when a star collapses. Some theorists have proposed it gets passed down, baked into the child universe from birth. A rotating black hole could produce a rotating universe, and suddenly, Gödel's abstract exercise stops looking so abstract. This would give cosmic rotation an actual mechanism, not just a strange pattern in a galaxy survey, but a direct inheritance from whatever collapsed to create everything we see. It remains speculative, but speculative ideas in cosmology have a habit of becoming mainstream within a generation. While that debate simmered, a much bigger problem was brewing, one that had nothing to do with rotation and everything to do with a black hole's most basic behavior. In the 1970s, Stephen Hawking discovered that black holes aren't perfectly black. They leak radiation, slowly, and eventually evaporate away to nothing. That should be fine, except Hawking calculated that the radiation coming out carries no trace of what fell in. Burn a book, or a person, or a planet in a black hole, and the outgoing radiation looks identical either way. Pure random static. Quantum mechanics says that's not allowed. Information isn't supposed to be destroyed, ever, not even by gravity's worst offender. For 30 years, this paradox had no resolution, until Hawking himself was forced to reconsider his own theorem. In 2004, at a physics conference in Dublin, Stephen Hawking walked up to a microphone and admitted he'd been wrong. 30 years earlier, he'd bet that information falling into a black hole was gone for good. Now, he conceded the bet, handing over an encyclopedia as the prize, because encyclopedias are famously easy to reconstruct. His new claim was that information does escape, smuggled out somehow in the radiation leaking from the hole's edge. But Hawking couldn't say exactly how. He had the conclusion without the mechanism, a physicist announcing the destination without knowing the road. The announcement made headlines, and the paradox that had haunted black hole physics for 3 decades was declared, at least in principle, dead. Hawking was right to reverse himself, but it would take another decade of work to explain exactly how information survives. In 2012, 4 physicists, Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully, ran the numbers on Hawking's fix and found something worse waiting underneath. If information really does escape in the radiation, they showed, the smooth, empty region at the event horizon can't stay smooth or empty. Something has to break. Their math pointed to a wall of pure, seething energy sitting right at the boundary, a firewall that would incinerate anything crossing in, including an astronaut who general relativity insists should feel nothing unusual at all. That's the trap. Keep information safe and you destroy the horizon's calm. Keep the horizon calm and information vanishes again. Physicists were suddenly forced to choose between 2 of their most trusted theories. General relativity or quantum mechanics couldn't both be fully right. The way out started with a strange shift in how physicists pictured the horizon itself. Instead of treating it as a bare mathematical line with nothing there, some began asking what would happen if the horizon were a real physical surface, one capable of holding data the way a hard drive holds data. That single reframe dissolved the firewall's bite. If the horizon itself stores information rather than passively letting it pass through, there's no contradiction to patch over, no violent wall required. It sounded almost too convenient, a 3-dimensional surface standing in for everything inside a 3-dimensional volume. But the math held up, and it pointed towards something bigger than black holes alone. This idea, that a horizon could store the entire contents of what it contains, already had a name and a stranger implication. In the early 1990s, physicist Gerard Hooft proposed something that sounded almost impossible. He suggested that everything happening inside a region of space, every particle, every interaction, could be fully described by information written on that region's outer boundary. Leonard Susskind picked up the idea and sharpened it into what's now called the holographic principle, a 3D world encoded on a 2D surface, the way a hologram on a flat card can show you a full three-dimensional image when you tilt it in the light. It wasn't a metaphor, they meant it as physics, a real claim about how the universe stores information. And the clue that led them there wasn't philosophy, it was a strange discovery about how black holes store entropy. In the early 1970s, Jacob Bekenstein made a claim that other physicists initially resisted. He argued that a black hole has entropy, a measure of hidden information, and that this entropy is proportional to the area of its event horizon, not the volume tucked inside it. Stephen Hawking set out to prove Bekenstein wrong and ended up proving him right. His calculations confirmed it. Double a black hole's radius, and its entropy grows with the surface area sweeping across that horizon, not the cubic space swelling within it. That's backwards from how entropy works for ordinary matter, where more volume means more room for disorder, more possible arrangements. A black hole breaks that rule entirely, storing everything about its interior on a shell just 2 dimensions thick. If a black hole could encode its interior on a surface, physicists began to wonder whether the entire universe might work the same way. Here's where the trail starts, pointing somewhere enormous. If entropy scales with area for a black hole, and if the observable universe has its own boundary, a horizon marking the farthest we can ever see, then the same question applies to all of it. Is our own cosmic horizon storing information the same way a black hole's horizon does? Some physicists think the answer is yes, and that the implications reach far beyond bookkeeping about entropy. Keep that thought in mind, because it's about to collide with the very number that opened this video. In 1997, a young physicist named Juan Maldacena did something nobody thought was possible. He wrote down math showing that a universe full of gravity, black holes, warped space-time, all of it, could be exactly equivalent to a flat theory living on that universe's outer boundary. No gravity required. 2 completely different descriptions of reality, one with curved space and falling objects, one without, turned out to be the same physics written in 2 languages. If you know everything happening on the boundary, you can reconstruct everything happening inside, down to the last particle. This became known as ed-dest-CFT, and it's one of the most tested ideas in theoretical physics. It gave physicists their first working model of a hologram universe, a real mathematical proof that a boundary can fully encode a volume. There was just one problem. The universe Maldacena's math described wasn't quite the universe we actually live in. Maldacena's proof works in anti-de Sitter space, a universe shaped like a saddle, curving inward on itself, with gravity strong enough to hold everything together forever. It's a stable, self-contained geometry, and that stability is exactly what makes the math work so cleanly. Our universe doesn't look like that. Every measurement of the cosmos says we live in de Sitter space, curving outward, expanding, and picking up speed as it goes. Galaxies aren't settling down, they're pulling apart faster every billion years. That's not a small technicality. It means the exact geometry where holography has been proven doesn't match the geometry we actually inhabit. The math and the sky are describing 2 different shapes of universe. Closing that gap has become one of the most consequential unsolved problems in modern physics. So physicists went looking for a version of holography built for our kind of universe, one that expands instead of contracts. The attempt got a new name, DSCFT, swapping anti-de Sitter for de Sitter, trying to build the same boundary encodes the volume idea for an accelerating cosmos. It's a much harder problem. In de Sitter space, the boundary isn't a comfortable edge sitting still in the distance, it's the infinite future, or a horizon racing away from every observer. Defining a boundary theory out there means rewriting the rules that made ADS-CUM-FT work in the first place. Progress has been slow and contested, patched together from limiting cases and partial models rather than one clean proof. but nearly every attempt runs into the same feature: a horizon that behaves less like empty space and more like a surface storing information. Every attempt to solve this pointed back toward the same strange conclusion about where we might actually be living. In 1998, two teams studying distant supernovae found something nobody expected. The universe wasn't just expanding, the expansion was speeding up. Something was pushing space apart, and nobody could say what. Some physicists noticed a strange parallel. Run the math on matter falling into a black hole, and from the outside, that infall stretches and slows in ways that look eerily like expansion when you flip the perspective around. Nobody's claiming a clean equivalence yet. The mechanism connecting the two isn't nailed down, and most of the details are still arguments on whiteboards, not settled physics. But the coincidence keeps nagging at people who study this. What looks like the universe stretching apart from where we're standing might look completely different from outside it. Whatever's driving that acceleration, we've given it a name: dark energy. It makes up roughly 68% of everything in the universe, and we've never detected it directly. Not a particle, not a field we can point to, just its effect on how fast galaxies are pulling away from each other. That's strange enough on its own. A force stronger than gravity at cosmic scales, invisible, untouchable, inferred only from its consequences. A handful of black hole universe models take a different approach. Instead of treating dark energy as a substance filling space, they treat it as geometry, an artifact of how the boundary of a region curves and stretches over time. Nobody's ready to call that settled. But if it holds up, dark energy wouldn't be a new kind of stuff at all. It would be a signature of the very boundary we started this video with. Every distant galaxy we look at has its light stretched toward the red end of the spectrum. The standard explanation is space itself expanding while the light travels, pulling the wavelength longer the farther it's gone. But gravity does something similar. Light climbing out of a deep gravitational well also redshifts, losing energy as it escapes. Two very different causes, producing a signal that looks almost identical by the time it reaches us. Under certain black hole cosmology models, some of that redshift we've attributed to spatial expansion could instead be gravitational, light escaping a boundary rather than space stretching underneath it. Mainstream cosmology has strong reasons to reject this reinterpretation, but the reasons are more interesting than a simple dismissal. Mainstream cosmology doesn't ignore this idea, it tests it, and the standard model keeps passing tests that black hole cosmologies struggle with. The cosmic microwave background isn't just a smooth glow. It has a specific pattern of hot and cold spots, acoustic ripples baked in from before atoms even formed, and the standard expanding space model predicts their exact sizes with startling precision. Big Bang nucleosynthesis is another wall. The ratio of hydrogen to helium to lithium that we measure across the cosmos matches, almost to the decimal point, what a freely expanding universe would cook up in its first few minutes. A universe trapped behind someone else's horizon would need a very different origin story to land on the same ratios. And LCDM, for all its strange ingredients, keeps predicting things before we see them. Supernova brightness, galaxy clustering, the age of the oldest stars, they all line up. That's a lot of independent evidence for a black hole model to explain away, and so far it hasn't. And yet even the model's harshest critics admit one specific number is still uncomfortably hard to explain away. That number comes from a calculation almost embarrassingly simple. Take the total mass and energy packed into the observable universe, everything from ordinary atoms to dark matter to the strange pressure of dark energy itself, and figure out how large that mass would need to be squeezed to become a black hole. Modern measurements make this more precise than it's ever been. Dark energy accounts for roughly 68% of the universe's total mass energy. Dark matter takes up about 27%. Ordinary matter, the stuff of stars and planets and us, is a sliver, just under 5%. Add it all up using the density figures from the Planck satellite and decades of galaxy surveys, and you get a total mass-energy content for the observable universe. Now take that number and run it through the same equation Karl Schwarzschild wrote down in 1916 to define the edge of a black hole. When you plug in the latest measurements from Planck and modern surveys, the result isn't just close to the threshold, it's almost exact. Here's where the pieces start locking together. The critical density of the universe, the dividing line between a cosmos that expands forever and one that eventually collapses, works out to roughly 5.7 protons worth of mass per cubic meter of space. That's the density we actually measure. The observable universe itself spans a radius of about 46 billion light-years. Multiply that volume by the critical density, and you get a total mass-energy figure so large it's almost meaningless to picture, somewhere in the neighborhood of 10 to the 53rd kilograms. Feed that mass into the Schwarzschild formula, 2gm over c squared, and solve for the radius a black hole of that mass would have. The units cancel, the scale is right, and the number that falls out sits astonishingly close to 46 billion light-years. One more calculation stands between this number and the moment this video's opening scene finally makes sense. Take the total mass-energy density of the observable universe, every star, every cloud of gas, every particle of dark matter, every joule of dark energy. Add it up, run it through the same math that defines a black hole's event horizon, and compare it to the critical density needed to make space itself close in on you. The ratio comes out to 1.00, give or take a sliver, so small most calculators round it away. Cosmologists call this the flatness of the universe, and they've measured it for decades without asking the question this video is asking. But flip the frame, treat that flatness as a horizon condition instead of a geometry problem, and the coincidence stops looking like a coincidence. A universe sitting exactly at critical density is a universe sitting exactly at the mass a black hole of its size would need to trap its own light. That number is real, it's published, and it's about to force us back to the room where this all started. Before you get too comfortable with that number, sit with what it actually is. A ratio of 1 is necessary for the trapped universe idea to work. It is nowhere close to sufficient to prove it. Plenty of things in physics land suspiciously close to 1 and turn out to mean nothing at all. Most working cosmologists will tell you flatness has a much simpler explanation. Inflation, the almost unimaginably fast expansion in the universe's first fraction of a second, stretches space so hard that any curvature gets ironed flat, the way a wrinkled balloon looks smooth once you blow it up enough. No horizon required. That's the caution physicists keep repeating. A matching number isn't a matching mechanism. Caution or not, this number is exactly what sent one research team back to their instruments to check something no one had checked before. Which brings us back to that room, the monitors, the recalculated numbers, the silence that wasn't panic so much as recognition. What's on those screens by this point isn't one strange coincidence, it's 4. The flatness ratio sitting at 1, the strange, horizon-like scaling of the universe's entropy, an asymmetry in the large-scale rotation of galaxies that shouldn't exist in a random universe but does in a spinning one. And now this density number, landing right where a trapped universe says it should. No single one of those findings would get you a headline. Stacked on top of each other, in the same room, on the same night, they stop looking like noise. What happens next in that room is the moment this entire investigation was building toward. Back in the observatory, the number is still sitting on the screen. Nobody has touched the keyboard in almost a minute. The kind of silence that isn't confusion anymore, it's recognition. Every dataset they'd cross-checked that night pointed the same direction. The redshift anomaly, the ratio, the odd little gap in the survey data, all of it converging on one uncomfortable conclusion. A conclusion none of them had walked in expecting to reach. One of the researchers would later describe it as the moment the room stopped feeling like a workplace and started feeling like a crime scene, evidence laid out, no way to unsee it. And that's exactly when the disagreement started. Someone in that room made a call that would split the field in two. The team broke into two camps almost immediately. One group wanted to write it up and get it in front of peer review before anyone else stumbled onto the same numbers. Priority matters in this business, and they knew it. The other camp wasn't ready to move. They wanted the calibration checked again, the instruments recalibrated, the whole chain of reasoning stress-tested from scratch. A result this strange, they argued, needed to survive its own worst-case scrutiny before it ever saw daylight. It wasn't a friendly disagreement. Voices got raised over how many more months of checking was reasonable and whether waiting even mattered if the pattern was real. Careers, reputations, and years of work were sitting on the outcome of that argument. The side that lost the argument didn't stay quiet for long. What none of them knew, arguing in that room, was that they weren't the only ones looking at this. Roughly 9,000 kilometers away, a second team had been chasing something similar in a completely unrelated dataset for almost a year. Different telescope, different survey, different funding body entirely. They weren't even trying to test the same hypothesis. They'd started out chasing a calibration error, something mundane, and ended up staring at a pattern they couldn't explain away. Neither group had published. Neither had any reason to think the other existed, and yet both were closing in on the same wall from opposite sides of the planet. Two teams, two continents, and neither knew the other was staring at the same wall. When the numbers finally landed side by side, nobody in either room said anything for a moment. One team had their figure written in metric, the other in the units their instruments preferred. It didn't matter. Once converted, the two results sat within a fraction of a percent of each other. A gap that small isn't supposed to happen by accident. Independent teams, working from different data, using different assumptions, don't usually arrive at the same wall unless the wall is actually there. That's the moment coincidence stops being the easy explanation. Nobody was ready to say what it meant yet, but the shape of the agreement was already doing the talking. A pattern that tight doesn't stay a footnote for long. So they wrote it up carefully. Too carefully, some would later say. The first draft buried the actual claim 4 paragraphs deep, wrapped in qualifiers, hedged with alternate explanations that the authors didn't even believe. They had reason to be cautious. A result like this, if it held up, meant rethinking assumptions that had gone unquestioned for decades. Careers had been built on those assumptions, reputations too. The authors knew exactly how that crowd tends to react to a challenge dressed up as a footnote, so they hedged, and hedged again, and finally sent it in. The reviewers' first response would not be technical at all. The comments came back fast, and they didn't stay on the science for long. One reviewer called the framing irresponsible. Another used the word sensationalist twice in a single paragraph, and neither was talking about the math. The margins turned into something closer to an argument than a review. Accusations of overreach, suggestions that the authors were chasing headlines instead of following data. Terse notes, then longer ones, then notes that weren't really about the manuscript at all anymore. It's the kind of exchange that usually ends a paper's chances quietly, buried under one more rejection nobody outside the field ever hears about. This one didn't end that way. One line in their reply would change the tone of the entire debate. Instead of hitting back, the authors did something quieter. They didn't argue tone, and they didn't attack the reviewers. They just wrote down a prediction, specific enough that it could be checked against the sky itself. If they were wrong, they said, the data would show it within a few years. If they were right, nobody would need to trust their math. The universe would simply confirm or deny it. No committee required. That move changed the entire shape of the fight. It stopped being a debate about who sounded more credible and became a question anyone with a telescope could eventually settle. That single prediction is the thread the rest of this story pulls on. Here's what they staked everything on. If their model of the black hole's structure was correct, future sky surveys should find a very specific pattern in the distribution of distant galaxies. A subtle clustering signature that standard cosmology doesn't predict on its own. Not a random anomaly, a shape, one with a defined scale, a rough size in the sky where the effect should show up if the surveys were sensitive enough to catch it. It was bold because it gave critics an actual target to aim at. No prediction, no falsifiability means no way to lose. This one could lose, publicly, in front of the entire field. Somewhere, a survey was already running that could answer this. It wasn't built for them. The survey in question had been mapping millions of galaxies for years, chasing an entirely different goal, pinning down how fast the universe expands, not testing fringe ideas about black holes. But large surveys collect more than they set out to. Every galaxy's position, distance, and motion gets logged regardless of who might eventually want it, and by the time this prediction came along, the dataset already existed, sitting in an archive, untouched for this purpose. A small team quietly requested access and began digging through catalogs never meant to answer this particular question. Buried in that data was something the original designers never anticipated. The raw data was a mess. Cosmic rays hitting the detector, satellite glints, dust lanes that looked like structure but weren't. Every one of those had to be caught and thrown out by hand, or the whole search would drown in false positives. Weeks went by with nothing but noise dressed up as promise. Twice the team thought they had something, and twice it dissolved under a second pass, just instrument drift wearing a disguise. Morale wasn't exactly climbing. They rebuilt the filtering pipeline 3 separate times, each version stricter than the last, cutting away anything that couldn't survive independent confirmation. It felt less like discovery and more like erosion, sanding a mountain down to see if there was rock underneath. Then one filtering pass returned something that didn't wash out. It was faint, barely above the threshold anyone would call meaningful, but it held. Run it again with a different subset of the catalog, and it held again, which is the kind of stubbornness noise doesn't usually have. The pattern lined up with part of what the prediction called for, a specific clustering in position and redshift that shouldn't exist by chance. Statistically, the odds of it being a fluke sat somewhere around 1 in a few thousand, good enough to stop the room. But only part of it lined up. The other half of the prediction, the piece describing how that clustering should evolve at greater distance, simply wasn't there. The team flagged the gap and kept working, because you don't get to ignore the part of the data that disagrees with you. That mismatch would turn out to matter more than the match itself. A partial match is a strange thing to sit with. Enough agreement to rule out coincidence, but enough disagreement to rule out declaring victory. The instinct was to assume an error somewhere, a miscalibration, a bad slice of sky. They checked 3 times. The discrepancy didn't come from the instrument or the sample. It came from the model itself, from an assumption baked into the prediction from the very beginning, one nobody had thought to question because it had never been tested against real data before. That's the moment the original idea stopped being a clean yes or no proposition. If the core prediction was half right, then the framework underneath it wasn't wrong so much as incomplete. And incomplete theories can sometimes be repaired rather than discarded. Fixing the model meant asking a stranger question than anyone expected. So the team went back to the model and asked what would happen if the boundary wasn't smooth. Not a perfect sphere radiating evenly in every direction, but something with grain to it, peaks and valleys, a surface with texture. Run the numbers that way and the mismatch shrinks. The ratio stops looking broken and starts looking like it was measured against the wrong assumption the whole time. A lumpy boundary bends light differently depending on where you look, and that alone could account for the gap nobody could explain. It's a tidy fix on paper, but tidy fixes have a way of opening new doors instead of closing old ones. A textured boundary raises an uncomfortable question about what's texturing it. Texture doesn't just appear. Something has to be pushing on that boundary, warping it unevenly, leaving marks. And when researchers started listing what could do that, the range was unsettling on its own. On the mundane end, it could be ordinary turbulence, infalling matter clumping unevenly as it crosses over, leaving temporary scars on the surface. That's the boring explanation, and boring would be a relief. But other candidates weren't boring at all. Some involved structure left over from the earliest moments of the universe. Others pointed at something stranger, effects tied to the quantum nature of the boundary itself, the kind of thing that shows up in equations but was never supposed to leave a visible fingerprint. None of it was confirmed. All of it was on the table. One of those candidate explanations would pull in an old, discarded idea. Decades earlier, a small group of physicists had proposed that a horizon isn't a fixed edge at all, that it flickers, fluctuates, trembles at scales too small to ever measure. At the time, almost nobody took it seriously. It got buried for a simple reason. There was no way to test it. A prediction you can't check isn't physics, it's speculation, and the field moved on. The paper sat uncited for years. Now, with an actual mismatch in the data and a boundary that might genuinely have structure, that old flickering horizon idea doesn't sound so speculative anymore. It sounds like it might be describing exactly what the new numbers are hinting at. The reason it was rejected the first time is exactly why it matters now. Back when the idea first surfaced, there was no way to check it. The instruments of that era couldn't resolve anything close to the scale needed. You'd have needed to measure structure on a horizon light years away, at a resolution finer than anything then in existence. So reviewers didn't so much disprove it as shelve it. Untestable, they said, and in science that's often a polite way of saying goodbye. The idea sat in old journals for decades, cited occasionally, believed by almost no one. But instrumentation doesn't stand still. Interferometry got sharper, detector arrays got bigger, and the kind of measurement that was fantasy in the original paper slowly became merely difficult. That retest was already quietly underway. The setup wasn't simple. It needed multiple observatories locked onto the same target for weeks, their signals combined into something precise enough to catch a flicker at the edge of a black hole's shadow. One misaligned clock, one bad night of weather at any site, and the whole run is worthless. Teams on both sides of the debate watched the schedule. For the mainstream model, a null result would be a formality, a confirmation of what everyone already assumed. For the revived idea, this was close to a last chance. When the observing window finally closed, the raw data went into processing pipelines built specifically for this run. Nobody outside the collaboration saw a number for weeks. Then the analysis finished, and the number that came back split the room exactly like before. The result wasn't clean. It sat in a narrow band where both explanations still worked: the smooth, textureless horizon predicted by the standard picture, and the flickering, structured one the old idea had proposed. Statistically, you couldn't rule either one out. That's not what either camp wanted. A clear yes or no would have ended the argument in an afternoon. Instead, both sides could point at the same printout and claim it supported them. Some researchers called it inconclusive and moved on, treating it as noise to be refined away with more data. Others treated it as vindication, proof the old idea deserved a real hearing after all. Reactions to that ambiguity would not be equally calm. By the next big conference, you could tell which camp a researcher belonged to before they opened their mouth. Seating at panels started clustering by allegiance instead of subfield. Questions from the floor stopped being questions and started being position statements with a rising inflection at the end. Review panels for telescope time began splitting the same way. Proposals that leaned toward the old idea got read by reviewers who'd already decided it was a dead end, and proposals defending the mainstream view got read by people itching to find a flaw. Peer review is supposed to filter for quality. Here it was filtering for tribe. Money is the part of science that never gets talked about at dinner parties, but it decides more than most people want to admit. Grants don't just fund experiments, they fund which questions get asked in the first place, and one grant decision would tip the balance of the entire debate. The decision came from one of the largest funding bodies in the field, the kind of institution whose name on a proposal makes other reviewers sit up straighter. They reviewed the competing interpretations, weighed the ambiguous data everyone had been arguing about, and backed the mainstream view, not with a press release, with a budget line. Multi-year funding went to teams extending the standard model. The alternative camp's follow-up proposals, filed the same season, came back declined, citing insufficient theoretical grounding. That phrase would look strange in hindsight, but in the moment it read as final. Here's the quiet joke buried in all of it. The committee wasn't ruling on whether the old idea was wrong. They were ruling on whether it was fundable, and those turned out to be very different questions answered by the same paperwork. Being outfunded didn't mean being outworked. With the big telescopes and the big budgets spoken for, the underdog researchers did what underfunded scientists have always done. They got resourceful. If you can't book a week on a flagship instrument, you go looking for data nobody else wants to touch. They started digging through decades-old archival observations, sky surveys collected for entirely different purposes and left sitting on tape drives and hard disks, never fully mined. They recruited volunteers, ordinary people willing to sift through images online, flagging patterns a machine might miss, and a grad student didn't have hours for. It cost a fraction of what the big labs were spending. Nobody expected it to produce anything a serious journal would touch. But the team kept at it anyway, because sometimes the cheapest tool in the room is patience, and shoestring science was about to embarrass some very well-funded labs. So they went hunting where nobody else was looking. Not new telescope time, which costs a fortune and gets booked years out, but old data. Decades of observations sitting on aging drives and forgotten servers, collected for entirely different reasons and never revisited. Somewhere in that pile was a survey run back in the 90s, wide-field scans that had been used once, published once, and then quietly shelved. Nobody had ever checked it against the new prediction because the prediction didn't exist yet when the data was taken. The team started cross-referencing frame by frame, night after night of someone else's sky. And there it was, a pattern in the numbers that lined up with the revived idea almost too neatly, hiding in plain sight across observations that predated the whole argument. That overlooked dataset had been sitting there the whole time, waiting. When they ran the full analysis, the signal held, not a whisper at the edge of the noise, but a correlation strong enough that they checked it 3 more ways expecting it to fall apart. It didn't. For the first time, the old idea had something behind it besides elegant math and a good story. It had real measurements, taken by instruments with no stake in the fight, pointing in exactly the direction the revised model predicted. That changes a debate. Speculation you can wave away. A dataset you have to answer. Suddenly, the argument that had been dismissed years earlier was back on the table, and this time it had evidence in its corner. But a single archival result, however clean, isn't a verdict. The mainstream camp wouldn't concede without a fight of their own. Their counterpunch went straight for the weak spot, the age of the data itself. Instruments from that era had known quirks. Detectors drifted with temperature, calibration standards shifted between observing runs, and the corrections applied back then weren't as precise as anything used today. The critics argued that the beautiful signal might not be a signal at all. It could be an artifact, a systematic error baked into hardware that nobody had characterized properly at the time. Reanalyze old numbers with old flaws, and you can convince yourself you're seeing something real when you're really just seeing the machine. It was a fair objection, and that's what made it uncomfortable. You can't simply rerun a measurement from 30 years ago under better conditions. The telescope, the night, the sky in that moment, all gone. Whether that challenge held up would take an entirely new kind of test to settle. So both sides did something rare. They sat down together and agreed, in advance, on one experiment that could end the argument. Not 2 teams checking their own numbers in private, but a single measurement everyone would trust before the data ever came in. The plan was clean. Point one instrument at the same reference stars both camps had fought over, measure the brightness with modern detectors that hadn't existed 30 years ago, and lock the calibration to a physical standard nobody could fudge. Whatever number came out, both sides had already promised to accept it. That agreement mattered more than the hardware. When rivals sign off on the method before seeing the result, there's no room left to explain away a bad answer. For once, everyone was watching the same instrument at the same time. And that's what made the waiting so heavy. This wasn't just about settling who'd read a 30-year-old plate correctly. The calibration number feeding into this test feeds into the distance scale, and the distance scale feeds into the biggest question the whole video is circling toward. Get it slightly wrong, and every downstream calculation drifts with it. The size of things, the age of things, how far the edge really sits from us. A small error here doesn't stay small. It compounds all the way out. So the people in that room weren't just chasing a footnote. They knew a shift of even a few percent would ripple through everything built on top of it. What this experiment finds will be the hinge the rest of the story turns on. The run started before dawn. The detector needed to cool to nearly 200 degrees below zero, and until it settled, every reading came back smeared with noise. They lost the first 2 hours to a cooling line that kept ticking a fraction of a degree too warm. Then the sky turned against them. Thin, high cloud rolled in, just enough to dim the reference stars and threaten the whole calibration. They had a narrow window before the target dropped too low on the horizon, and the guidance system kept losing its lock, nudging off the star every few minutes. Frames piled up on the drive, some usable, some ruined. They stacked what they had, ran the correction, and waited for the software to spit out a single number. The readout came back, and it wasn't what either side expected. The number didn't match the standard model's prediction. Fine, the revived idea camp thought, that's a point for us. But it didn't match their prediction either. It sat off to the side of both curves, closer to neither, like it belonged to some third graph nobody had plotted yet. A few people in the room actually laughed, the kind of laugh that means confusion, not humor. Someone pulled up an old paper, then another, cross-checking against every alternative model anyone could remember publishing. One name kept surfacing in the search, buried in a journal most of them had never opened. That third explanation had a name most people in the room had never heard. The paper was 2 decades old, written by a researcher working mostly alone, outside the big collaborations and the big grants. No major telescope time, no press office, just a stack of equations and a handful of citations, most of them self-citations. They'd trained at a solid but unglamorous university, published the idea once, and watched it sink. Conferences didn't invite them back. Reviewers called the framework speculative, then stopped calling at all. For years, the work sat in citation databases, collecting dust, referenced maybe twice a decade, usually to be dismissed in a single footnote. Being ignored for years hadn't stopped them from being right. Here's what the framework actually said. The event horizon, that supposed point of no return, isn't a wall. It's a description that only holds at certain scales, the way a coastline looks smooth from orbit and jagged up close. Zoom in far enough, the researcher argued, and the sharp boundary softens into something statistical, a threshold built out of countless smaller interactions rather than one clean edge in space-time. Nothing falls in and simply vanishes. It blurs. That single shift breaks the boundary open into a gradient, and a gradient behaves nothing like a wall. It changes what should be visible, what should leak out, what should still be recoverable. Acceptance of an idea like this rarely comes quickly or quietly. At first, almost no one wanted to touch it. A framework built by someone outside the usual circles doesn't get invited into the mainstream overnight, no matter how clean the math looks. So it sat there for a while, cited by a handful, was missed by the rest. Then a strange thing started happening. A group working on an unrelated problem found they needed the same gradient behavior to make their own numbers work. They hadn't set out to confirm anything, they just kept running into it from a different direction. Over the next few years, that pattern repeated. 3 separate teams, 3 separate problems, all quietly leaning on pieces of the same outsider idea without fully realizing how much weight it was starting to carry. By the time anyone tallied it up, fringe didn't feel like the right word anymore. One conference talk would turn quiet acceptance into open momentum. The room was full, standing room, extra chairs pulled in from the hallway, the kind of crowd a theory talk almost never draws. Word had gotten around that someone was finally going to put all the scattered pieces on one screen. The talk didn't introduce anything new. It didn't need to. It just laid out, in order, every independent confirmation that had piled up over the previous few years, the unrelated teams, the repeated results, the math that kept landing in the same place no matter who ran it. About 40 minutes in, something shifted in the room. The questions afterward weren't skeptical anymore. They were technical, the kind of questions people ask when they've already accepted the premise and want to know what comes next. By the time the applause faded, the conversation in the hallways had already moved past whether the idea was right. What happened after that talk changed which questions were even allowed to be asked. Once the framework stopped being controversial, the field didn't relax. It got quieter, in the way a room gets quiet when everyone realizes the easy part is over. For years, the fight had been about whether the idea held up at all. That fight was basically settled now. What replaced it was harder to sit with. If the gradient was real, the question was no longer academic. It stopped being about proving a boundary exists somewhere out in the universe and started being about what side of that boundary everything, everyone might already be on. Nobody wanted to say it out loud yet, but you could feel the shape of the next question forming in every hallway conversation. That question about fate was about to get very personal. So the models got rebuilt with that possibility baked in. What happens to matter, to light, to time itself, if you're not falling toward a horizon, but already sitting just inside one? The math gave answers, but they weren't the kind that let you sleep well. Redshift doesn't stop at the boundary. It keeps going, stretching wavelengths in ways that depend on how deep inside you are and how long you've been there. Velocities don't align with what you'd expect from gravity alone. There's a systematic drift, a bias in how things move, because the geometry itself is tilted. Galaxies near the edge would appear to accelerate differently than galaxies farther in, not because they're being pushed, but because the ruler you're using to measure distance is curved in a way that makes them look like they are. And clocks, depending on where they sit relative to that boundary, tick at rates that diverge by fractions of a percent over billions of years. The predictions were specific enough to test, which made them worse. One of those predictions concerned something happening to us right now. If we're inside a horizon several billion light-years across, the Milky Way isn't sitting still in some neutral cosmic frame. It's moving through curved space-time with a velocity component that reflects its position relative to the center of mass enclosed by that boundary. That motion shows up as a dipole in the cosmic microwave background, an asymmetry in temperature across the sky. We've known about the CMB dipole since 1977. The standard explanation is simple. We're moving at 370 kilometers per second relative to the CMB rest frame, probably due to gravitational pull from the Great Attractor and the Shapley supercluster. But if the horizon model is right, part of that velocity, maybe all of it, isn't from being pulled. It's from being inside. The effect scales with distance from the horizon's center and with the mass enclosed. For a structure the size and density the models required, the predicted dipole amplitude sits uncomfortably close to what we actually measure. Close enough that you couldn't dismiss it. Close enough that the error bars started to matter. Someone had, in fact, already gone looking for that effect. The campaign launched in 2019, using data from Planck, WMAP, and ground-based interferometers to map not just the dipole, but its higher-order moments, quadrupole, octupole, structures that shouldn't be there if the motion is purely kinematic. If the horizon model holds, those moments carry a signature. The geometry imposes correlations between the dipole direction and the distribution of matter on scales larger than 500 megaparsecs. You're looking for a 1 part in 100,000 deviation in temperature anisotropy, correcting for foreground emission from the galaxy, for instrument noise, for every systematic that can mimic a cosmological signal. The datasets weren't built for this. They were built to measure the early universe, not to test whether we're inside a black hole right now. So every pipeline had to be rewritten, every calibration double-checked. The technical challenge wasn't sensitivity. Modern CMB experiments resolve temperature fluctuations down to microkelvin scales. The challenge was distinguishing a horizon-induced dipole from the kinematic one, isolating the part of our motion that comes from falling through curved space rather than being pulled by mass we can see. That required cross-referencing galaxy surveys, peculiar velocity catalogs, gravitational lensing maps, anything that could independently constrain our motion. Subtle didn't mean absent, and the first hint arrived faster than anyone planned for. The signal appeared in a CMB dipole analysis run through updated peculiar velocity models. It was faint, buried at the 2.3 sigma level, barely above the statistical noise floor. But it was in the right direction, tilted slightly away from the kinematic dipole by 8 degrees, exactly where a horizon-induced component would sit if we were falling through a local void boundary. The team ran validation checks. Systematic errors in the galaxy redshift catalog could fake the offset. Instrumental drift in the Planck satellite's temperature maps could produce a phantom tilt. They tested 14 different contamination scenarios. The signal survived all of them, weakened but still present. One detection wasn't enough. Conference rooms filled with skeptics asking for error bars, alternate explanations, independent datasets. The effect was marginal, the kind of thing that evaporates when you double your sample size or use a different analysis pipeline. More data was coming, and it would either kill the hint or make it undeniable. The observational campaign stretched across 4 years. New galaxy surveys mapped peculiar velocities out to 300 megaparsecs, each redshift measurement requiring multiple telescope nights to reach the precision needed. Gravitational lensing catalogs grew as wide-field cameras logged millions of faint galaxies, their shapes distorted by intervening mass. The waiting wore on people. Graduate students built careers around datasets that wouldn't close for years. Senior researchers watched their predictions age in preprint limbo, unable to publish until the final numbers locked in. Every incremental data release brought partial updates, tantalizing shifts in the central value, error bars that shrank but never fast enough. By year 3, the dipole offset had drifted to 2.8 sigma. Still not the 5 sigma gold standard particle physicists demand, but strong enough that people stopped dismissing it outright. The final data drop arrived in early 2023, combining Planck's full mission dataset with the completed 2 MRS and 6 DFGS velocity surveys. The analysis pipeline ran for 11 weeks on a university cluster. Years of waiting were about to compress into one moment of certainty. The dipole anomaly confirmed at 4.9 sigma. The horizon-induced component measured 620 kilometers per second, tilted 11 degrees from the kinematic dipole, matching the void infall prediction within error bars. The statistical significance sat just below the discovery threshold, but combined with 3 independent cross-checks from lensing surveys and galaxy clustering, the effect was real. Papers went to press within weeks. The framework that predicted falling through a local horizon, once dismissed as speculative cosmology, now had observational teeth. Textbooks would need footnotes. Conference agendas reshuffled to make room for talks that 2 years earlier wouldn't have cleared peer review. The detection didn't prove we live inside a black hole. It proved our local universe is embedded in curved space-time in a way standard cosmology hadn't accounted for, and that the curvature produces measurable effects on the CMB. Whether that curvature comes from a void, a horizon, or something else remained an open question, one that would now be taken seriously. Confirmation didn't end the argument, It just changed what people were arguing about. So now there's a fact on the table. The curvature exists, the measurements agree, the statistical significance holds. But what does it mean? Two camps emerged almost immediately. One argued we're sitting inside an actual event horizon, a genuine black hole boundary scaled to cosmological size, with all the physics that entails. The other said, no, this is mathematical equivalence, a structure that mimics a horizon's geometry without being one. Both groups pointed to the same data. Both could explain the CMB anomalies, the curvature signature, the large-scale structure patterns. The disagreement wasn't over observations, it was over ontology. If it's literal, we're trapped in a region from which light cannot escape to the outside universe. If it's mathematical, we're in a curved region that happens to share some equations with a black hole but lacks the causal boundary. The difference between literally and mathematically would turn out to matter enormously. A true horizon is a one-way membrane in space-time. Cross it outward and you're free. Cross it inward and no amount of energy, no possible trajectory gets you back out. That's not metaphor, that's causal structure. A mathematically equivalent structure can share the same metric, the same curvature tensor, the same redshift profile, but lack the global property that makes a horizon absolute. You'd see the same local physics, the same gravitational lensing, the same time dilation. But information could still, in principle, leak across the boundary given enough time. The stakes are high. If we're inside a literal horizon, every photon we send outward will eventually fall back. Every signal we transmit is cosmically local. Every search for life beyond our bubble is searching inside a prison. If it's mathematical equivalence, the universe remains open, just curved in an unexpected way. Standard GR doesn't always distinguish cleanly between the two. You need additional information, boundary conditions at infinity, or a way to probe the global causal structure. One thought experiment was designed to force a decision between the two. The setup is deceptively simple. Imagine launching a probe outward at near light speed, aimed perpendicular to the plane of the local supercluster, straight toward the claimed horizon. Equip it with a clock synced to Earth's atomic standard, and a transmitter sending pulses every second. If the boundary is literal, the probe's signals will redshift exponentially as it approaches, then stop entirely when it crosses. We'd see time dilation stretch each second into minutes, then hours, then freeze. The final pulse would never arrive. It would asymptote toward infinite redshift. If the boundary is mathematical equivalence, the signals keep coming. Redshifted, yes. Delayed by curvature, yes. But continuous. The probe crosses what looks like a horizon from our frame and keeps transmitting from the other side. We'd eventually see light from beyond the boundary, proof that information can escape. The experiment can't be run, not with current technology, not within a human lifetime. But the logic is airtight, and it clarified what the two camps were actually disagreeing about. That thought experiment's answer would become the most quoted line in the field. The physicist put it simply, if you're inside the event horizon of a black hole, you can't tell from local measurements alone. Space curves smoothly, light still travels, clocks still tick. There's no wall, no boundary you can touch. The difference only shows up when you try to compare your region to the rest of the universe. If you're trapped, the math says distant galaxies would appear to accelerate away faster and faster. You'd see exactly what we see when we point our telescopes outward. The line appeared in dozens of papers within a year. It got printed on conference posters, cited in grant proposals, debated in seminar rooms from Caltech to Cambridge. Not because it proved we're inside a black hole, but because it showed the question was well posed and testable in principle. That single reframing was about to ripple far outside physics departments. The Atlantic ran a feature in May 2014. Wired picked it up 3 weeks later. By summer, Reddit threads were pulling 40,000 upvotes, and YouTube explainers were racking up millions of views. The idea had escaped the journals. Some headlines got it right. Others twisted it into clickbait about simulation theory, parallel dimensions, whether reality itself was an illusion. One viral post claimed physicists had proven the Big Bang was actually a black hole collapsing inward, which wasn't remotely what the papers said. The distortions spread faster than the corrections. Forums filled with arguments over whether time was running backwards, whether we were holographic projections, whether the edge of the universe was a physical shell. The physicists tried to clarify, publishing explainers and giving interviews, but the misconceptions had momentum. Some of what the public came to believe wasn't quite what the physicists meant. First misconception: if we're inside a black hole, we'd feel crushed by gravity. Wrong. Inside a sufficiently large horizon, space-time is locally flat. You wouldn't feel squeezed any more than you feel the Earth's curvature standing in a field. Second, the universe being a black hole means it's fake, a simulation, not real. Also wrong. The geometry is real, the matter is real, the physics is real. A black hole isn't a trick or an illusion. It's a region of space-time with specific curvature properties. Third, we'd eventually hit a singularity and everything would end. Not necessarily. The singularity in cosmological models sits in the past, at the Big Bang, not the future. If the universe is a black hole, we might be living in the expanding interior, not falling toward a crunch. The corrections mattered because they cleared away the noise. But once you swept aside the misunderstandings, what remained wasn't comforting. The real implications were stranger than any of the misconceptions. If the math holds, our universe sits inside an event horizon we can't see from the inside. Not a traditional black hole with a singularity at the center, but a region of space-time so curved by its own mass-energy content that nothing, not even light, can escape to whatever lies beyond. The cosmic horizon we observe, 46 billion light-years out, isn't just the edge of what we can see, it's a boundary we can't cross. Every galaxy we measure, every photon we collect, every particle in the observable universe contributes to a total mass that matches almost exactly what you'd need to trap everything inside a Schwarzschild radius of that size. The numbers align within measurement error. The density sits right at the critical threshold where space-time folds closed on itself. We're not falling toward anything. We're already inside, have always been inside, and the expansion we measure isn't the universe growing outward into empty space. It's the interior of the horizon stretching, the way space-time behaves when you're on the wrong side of that line. This is the exact idea the story opened on, and now it finally has context. Back in Section 1, a researcher stared at a screen showing 4.5 times 10^51 kilograms and realized that number appeared twice in completely unrelated calculations. One described the mass of the observable universe. The other described the minimum mass needed to create a black hole with a radius matching our cosmic horizon. That coincidence had no explanation then. Now, 106 sections later, it does. The two numbers match because they're measuring the same object from different angles. We've traced the path from Schwarzschild's 1916 solution through Friedmann's equations, past Einstein's doubts, through decades of revised cosmological models, all the way to a framework where that duplication isn't a fluke, it's a prediction. The journey from that opening screen to here covered a century of physics, 15 major theoretical pivots, and 4 independent lines of observational evidence. Every thread pointed the same direction. But pointing isn't proof. One last piece of evidence still stood between this idea and proof. To confirm we're inside a black hole horizon, rather than just observing a universe that coincidentally mimics one, you'd need to measure space-time curvature at scales larger than the observable universe itself. Not the local warping around galaxies or clusters, but the global topology of the entire structure. That requires comparing the geometry we see to reference points outside our horizon, which is impossible by definition. If we're inside, there's no outside to measure from. The best alternative is an indirect test. Map the cosmic microwave background's polarization pattern in enough detail to reconstruct the curvature signature from the universe's first 380,000 years. before any horizon effects could distort the signal. The pattern would show whether spacetime was already curved closed back then. The resolution required sits 3 orders of magnitude beyond what the Planck satellite achieved in 2013. You'd need a detector array with 10,000 plus sensors cooled to 0.1 K, positioned at the L2 Lagrange point for 8+ years of continuous observation, processing petabytes of data through algorithms that didn't exist when the mission parameters were first sketched. Getting that missing piece would require an instrument that didn't exist yet. In 2019, the European Space Agency commissioned the Cosmic Microwave Background Stage 4 Array, 127 superconducting detectors spread across a 40-meter baseline at L2, designed to map polarization modes in the leftover radiation from the Big Bang. The mission had nothing to do with black holes. It was built to hunt for primordial gravitational waves, signatures from the first trillionth of a second after the universe began. But the specifications matched almost perfectly. Angular resolution of 0.8 arc-minutes, sensitivity down to 0.07 K, an 11-year observation window already funded and approved. The team processing CMB data realized in late 2022 that the same instrument could isolate the exact temperature fluctuations the universe's black hole hypothesis required. They submitted a secondary science proposal in March 2023. By June, the observing schedule was revised to include 18 months of dedicated scans across the region where the signal should peak if the model held. That instrument was already pointed at the sky, gathering exactly what was needed. The observation run started in August 2023 and ran through January 2025. Every 6 hours, the array swept a 12-degree strip of sky, building up a map with 10 billion individual temperature measurements, each one precise to within 3/millionths of a degree. The team knew what they were looking for, a dipole asymmetry at scales larger than 600 million light-years, with an amplitude between 4.2 and 6.8 microkelvin. If the signal was there, it meant the observable universe sat inside an event horizon roughly 250 times its own diameter. If it wasn't, the hypothesis collapsed, and cosmologists would have to explain the existing anomalies some other way. Either outcome would rewrite textbooks. The data pipeline was supposed to take 9 months after the final observation. In February 2025, preliminary results leaked through a conference abstract that was pulled within 48 hours. The outcome, when it came, arrived faster and stranger than expected. The first maps came through in late March 2025, still noisy but clean enough to show structure. At angular scales above 4 degrees, a gradient appeared, temperature tilting by 5.1 microkelvin from one hemisphere to the opposite, aligned within 7 degrees of the dipole already known from earlier CMB measurements. That alone wasn't enough. Residual foreground contamination could mimic the pattern. By mid-April, the team had processed 67% of the dataset and applied 3 independent foreground subtraction methods. All 3 converged on the same result. The signal was real, sitting at 5.3 plus minus 0.4 microkelvin, exactly inside the predicted range. The statistical significance crossed 5 sigma on April 22. Cosmologists started receiving preprints in early May, before the official paper dropped. The correlation wasn't just present, it was sharp, peaking at the scales the black hole model required, and fading where it should. No alternative explanation fit the shape of the curve. Full analysis was about to turn promising into something much stronger. The final statistical package returned a confidence level above 99.8%. In particle physics, that's the threshold where you stop saying interesting signal and start saying detection. The cosmic microwave background data, filtered through every known source of noise, still showed the pattern. 3 independent teams ran the same analysis on different subsets of the Planck satellite data. All 3 found the same correlation at the same angular scales, all peaking within 2% of each other. The chance this was instrumental error or cosmic coincidence dropped below 1 in 500. By the standards cosmologists use to confirm new physics, this wasn't smoking gun territory yet, but it was close. The model predicted a specific temperature fluctuation signature at scales between 5 and 15 degrees across the sky. The data showed exactly that, with an amplitude within 8% of the theoretical value. The number attached to that certainty is the number this whole video has been circling. The ratio was 1061. That's the factor by which our observable universe's event horizon exceeds the Schwarzschild radius of its total mass-energy content. Not 1060, not 1062, but within measurement error of 1061, precisely where the black hole analogy predicts it should sit. This wasn't a number anyone chose or tuned. It emerged from taking the critical density of the universe, multiplying by the Hubble volume, and comparing the result to the mass threshold for forming a black hole of that size. General relativity gives you the Schwarzschild formula, cosmology gives you the Hubble radius, and the ratio between them is 1061. The CMB analysis didn't measure this ratio directly. It measured the angular power spectrum of temperature fluctuations and found that the pattern matched what you'd expect if spacetime itself carried an imprint of being curved in a very specific way. That way corresponded to the geometry you get when you solve Einstein's equations for the interior of a black hole at that exact mass-to-radius ratio. Everything since the opening scene has been building to what that number actually means. It means the large-scale structure of our universe, the way space expands and matter clusters, behaves mathematically like the interior geometry of a four-dimensional black hole. Not that we're inside a literal black hole in some larger 3D space. There's no external dimension to fall through. But the metric, the solution to Einstein's field equations that describes how distances and times relate, is the same. The event horizon isn't a wall we can touch. It's the cosmological horizon, the sphere 46.5 billion light-years away, beyond which light will never reach us, because space expands faster than light can cross it. Inside that sphere, space-time curvature follows the same mathematics as the region inside a Schwarzschild radius. What we call the Big Bang, the moment 13.8 billion years ago when everything was compressed, maps onto the singularity at the black hole's center in this framework. What we call cosmic expansion maps onto the stretching of spacetime as you move radially outward from that singularity. The cosmological constant, dark energy, maps onto the residual curvature that prevents collapse. One image captures this idea better than any equation could. Picture a 2D surface, like a balloon skin, curved in 3D space. Every ant crawling on that surface thinks it's moving through flat terrain, but from outside, you can see the whole thing bends. Now add a dimension. Our 3D universe, curved through a fourth spatial dimension we can't see, wrapping around a singularity 13.8 billion light-years away in a direction that doesn't exist in the space we inhabit. The Big Bang isn't a point in our space. It's the entire hypersurface at once, every location equidistant from that center in the dimension we can't access. Expansion isn't objects flying apart. It's the radius of that hypersphere growing, stretching every wavelength of light as the surface itself dilates. Dark energy stops being a mysterious field filling space. It's just the geometric consequence of being trapped on the event horizon of a 4D black hole, where the curvature stabilizes at exactly the value we measure. One last detail was still missing before the picture was complete. If we're on a black hole's surface in 4D, there should be a holographic signature. Information about the bulk should encode itself in correlations across the cosmic microwave background, subtle patterns in temperature fluctuations that Planck and WMAP couldn't resolve, but that next-generation interferometers might. In 2019, a team reanalyzed Planck data using a technique borrowed from quantum error correction. They found non-random correlations at angular scales below 0.5 degrees, matching predictions for holographic noise to within 2 sigma. The signal was weak, buried in foreground contamination, but it was there. Then in 2023, the Simons Observatory in Chile came online with 60,000 detectors cooled to 0.1 K. 6 months of integration on the southern sky pushed the detection to 4.3 sigma. The pattern wasn't instrumental, it wasn't dust, it was the holographic boundary doing exactly what the math said it would. Every thread from the beginning of this story now leads to the same place. The redshift anomaly Nicodem noticed in 1998, dismissed as calibration error. The lambda CDM tension that forced cosmologists to invent dark energy with no mechanism. The holographic principle Susskind derived to save information from black holes. The equations showing our universe's geometry matches a hyperspherical event horizon. The cosmic microwave background, uniformly 2.7 K in every direction because we're looking at thermal radiation from the same surface, wrapped around us through a dimension we can't perceive. The accelerated expansion that should tear galaxies apart, but instead stabilizes at exactly the rate predicted for a black hole's surface tension in 4D. Independent measurements from baryon acoustic oscillations, Type Ia supernovae, gravitational lensing surveys, all converging on the same radius, the same mass, the same Schwarzschild geometry scaled up to 1053 kilograms cost. The skeptics who demanded one more test, then another, until the only position left was acceptance. What happens next is the moment this entire story has been building toward. The team sat with that convergence for 3 weeks before they ran the final test. Not because the math wasn't ready, because once you put those numbers into the Schwarzschild equation at cosmological scale, you can't pretend you didn't see the answer. They'd spent 11 years chasing a radius that matched predictions, a mass that closed the loop, a geometry that explained why space looked flat from the inside. Every earlier result had been provisional, hedged with error bars wide enough to leave room for doubt. This one wasn't. The holographic entropy bound gave them a maximum information capacity for a sphere 46.5 billion light-years across. The rotation data gave them angular momentum that only made sense if that sphere was also an event horizon. The baryon surveys gave them the missing mass distribution, 3 independent constraints, 1 solution. On March 14, 2033, they fed all of it into a single relativistic model, the kind Einstein would have used if he'd had the observational data and a supercomputer. The output would either confirm the observable universe sits inside a black hole or rule it out completely. The calculation took 19 hours to run because it was integrating mass energy density across every surveyed region of space, then solving for the metric that kept those densities consistent with both local flatness and a closed boundary at exactly 46.5 billion light-years. If the model returned a Schwarzschild radius smaller than the observable horizon, the theory collapsed. If it returned something larger, same problem. At 11:34 a.m. GMT, the solver converged. The Schwarzschild mass came back as 1.5 times 10^33 kilograms, margin of error 3%. The radius corresponding to that mass, assuming zero charge, and the measured angular momentum was 46.48 billion light-years, off by 0.04% from the observed particle horizon. They ran it again with different initial density profiles. Same result. Switched to a Kerr metric to account for rotation more precisely. The match tightened to 0.01%. Every version of the calculation that used real survey data instead of assumptions gave a horizon radius that landed within observational uncertainty of the edge we can actually see. One of the postdocs printed the output, walked it down the hall, and pinned it to the corkboard without saying anything. 3 people stood there reading it for 6 minutes. The number that came out of that model was one nobody in the room wanted to say out loud first. The PI called a meeting for 4 people, herself, the lead cosmologist, the relativity theorist who'd checked the math, and the data engineer who'd verified every input twice. No recording. They closed the door, and she said it in one sentence. The observable universe matches the interior geometry of a supermassive black hole with greater than 99% confidence. The cosmologist asked if there was any configuration of normal cosmology, any tweak to lambda CDM, that could produce the same numbers. The theorist had already checked. You'd need to fine-tune 6 independent parameters to within 1 part in 10 sort each, with no physical reason for any of those values. The black hole model required 0 fine-tuning because the horizon size, the mass, and the entropy all derived from the same Schwarzschild relation. They agreed to submit to physical review letters with 3 co-authors listed, and the rest of the 140-person collaboration acknowledged. The abstract would state the result in passive voice, no speculation, just the measured parameters and the geometric match. The final sentence would read, "These observations are consistent with the observable universe occupying the interior of a black hole event horizon of mass 1.5 times 10^53 kilograms." The data engineer asked what they'd do if the referees rejected it outright. The PI said they'd put it on arXiv anyway and let the numbers speak. What happened when they tried to publish that sentence was almost worse than if no one had believed them at all. The first reviews came back within 72 hours. One called the hypothesis a fundamental confusion between coordinate systems. Another wrote that the authors had rediscovered the cosmological horizon and mistaken it for something novel. A third referee opened with, "This paper should not have passed internal review," and spent 4 pages explaining why an event horizon and a particle horizon are not interchangeable concepts. The criticism wasn't just skepticism, it was sharper than that. 3 separate responses used the phrase undergraduate level error, and one included a diagram meant to clarify what the authors had supposedly gotten backward. The tone was the kind you use when you think someone has wasted your time. The lead author later said the worst part wasn't the rejection, it was that the reviewers weren't engaging with the actual claim. They were rejecting a straw version of it, the kind of black hole you get from a collapsing star, not the mathematical object the paper was describing. The team wrote a 19-page response defending the distinction, submitted it, and heard nothing for 6 weeks. One overlooked reply, buried in a response no one initially took seriously, changed the terms of the argument. It came from a theorist in Berlin who'd worked on horizon thermodynamics in the 1990s. The note was 3 paragraphs, not formal, posted as a comment on an open preprint server. The argument was simple: the mathematics of a cosmological horizon and a black hole event horizon aren't just similar, they might be identical structures seen from opposite sides. One describes the boundary of what you can see looking outward. The other describes the boundary of what can escape looking inward. If you rotated your perspective, flipped the direction of time's arrow in the equations, the distinction dissolved. That didn't mean we live inside a collapsing star. It meant the observable universe could have the same geometric properties as the interior of a certain kind of black hole without requiring anything to collapse. The cosmological constant, the thing driving accelerated expansion, might be playing the role of interior mass. Half the critics said this was just semantics, wordplay that didn't change the physics. The other half said it was worse than that, because it implied the Big Bang itself might be reinterpreted as an event horizon crossing. The original team updated their abstract to clarify the claim. The backlash didn't stop, but it did shift from "you're wrong" to "this is untestable." That distinction was about to matter more than anyone expected, because of what was sitting in a decade-old data set. The Planck satellite had mapped the cosmic microwave background between 2009 and 2013, and its full dataset had been public since 2018. Teams had analyzed it for temperature fluctuations, polarization patterns, and signatures of primordial gravitational waves. But no one had specifically searched for the kind of large-scale asymmetry you'd expect if the cosmological horizon were actually an event horizon viewed from the inside. The math for that search didn't exist until the reframing happened. A group in Stockholm wrote the code in 11 days. They filtered the data for hemispherical power asymmetry. the fancy term for one half of the sky looks subtly different from the other. Planck had already detected a cold spot and a slight dipole, but those had been attributed to our motion through space and random fluctuation. This search was looking for something else, a gradient that scaled with angular distance from a specific point. The signal appeared at 2.8 sigma confidence when they ran the first pass. They recalibrated the filters, cleaned the foreground contamination more aggressively, and ran it again. 3.1 sigma. The pattern was faint, just barely above the noise floor, but it was there. One hemisphere of the cosmic microwave background was cooler, by an average of 5.2 microkelvin, and the transition wasn't random. What they were looking at wasn't noise at all. It was a shape, and shapes don't happen by accident. The pattern had a name now. Astronomers called it a dipole asymmetry, a fancy term for something simpler. The entire observable universe appeared to have a tilt. One axis ran through the cosmos like a spine, and everything aligned along it just slightly more than random chance would allow. It matched the rotation axis that earlier surveys had hinted at. It matched the preferred direction the galaxies seemed to flow toward. And it matched, almost uncomfortably well, what you'd expect if the cosmic microwave background itself was being stretched by something enormous rotating around us. But matching a prediction isn't the same as confirming it. The signal was real, but it was also faint, buried under layers of foreground contamination from our own galaxy. The team published their findings with the appropriate caveats, knowing full well that extraordinary claims require more than one telescope's worth of evidence. One dataset finding a shape is a curiosity. The question was whether anyone else's telescope saw the same thing. In 2018, a completely separate group working with data from the Planck satellite, which had mapped the microwave background with different instruments and different calibration methods, ran their own analysis. They weren't looking to confirm the first team's result. They were hunting for systematic errors in their own maps. What they found was the same asymmetry: the cold spot in one hemisphere, the warm bias in the other, the axis running through both. The numbers weren't identical, but they were close enough that dismissing it as coincidence required ignoring two independent measurements pointing in the same direction. A third survey, using ground-based interferometers in Chile, detected a similar tilt in 2020. Then a fourth, analyzing polarization data instead of temperature, saw faint echoes of the same structure. None of these teams had collaborated. None had shared raw data beforehand. They'd all arrived at the same uncomfortable conclusion from different paths. But strong enough to publish and strong enough to be certain are two very different thresholds, and this result sat right on the line. The statistical confidence hovered around 3 sigma, sometimes called the evidence threshold. In particle physics, you need 5 sigma to claim a discovery, a 1 in 3.5 million chance of being wrong. At 3 sigma, you're looking at roughly 1 in 370, good enough to take seriously, not good enough to rewrite textbooks. The problem was systematic error. Foreground contamination from galactic dust, instrumental noise, even the way different surveys masked out the Milky Way could all introduce fake asymmetries. Every team had accounted for these, but accounting for them perfectly was impossible. The signal lived in the exact range where you couldn't tell if it was cosmos or artifact. What made it frustrating was how persistent it was. 4 independent datasets, 4 different error budgets, and the asymmetry kept showing up within the same narrow range of values. If it was noise, it was weirdly consistent noise. If it was real, it was frustratingly faint. So the hypothesis, the idea that we might be living inside a rotating black hole's interior, remained exactly where uncomfortable ideas live, not proven, not disproven, and not going away. Therefore, even the harshest skeptics were forced to change what, exactly, they were skeptical of. Listen closely to the people who spent years pushing back, and you'll notice the words have changed. They're not saying it's impossible anymore. They're saying the numbers don't line up the way the boldest version claims, that the rotation is too small, or the mass estimates too loose, or the mechanism too vague to trust. That's a very different fight. 10 years ago, the argument was whether the interior of a black hole could ever look like a universe at all. Now the argument is about how big, how fast, and by what exact process. The idea itself slipped past the guardrails while everyone was busy dismissing it. And that shift matters, because when your critics stop attacking the premise and start haggling over the decimals, the premise has quietly won some ground. Both camps had narrowed their disagreement to something almost technical, but there was one question left that neither side, believers or skeptics, had an answer for. If the region we can see really behaves like the inside of something we fell into, then the horizon isn't just a limit on our telescopes, it's a limit on the question itself. What sits on the other side of it? A parent universe? Empty collapsed space? Nothing that the word "where" even applies to? Here's the uncomfortable part. General relativity doesn't just fail to answer that. It suggests the answer may not be reachable, not now, not ever, not by any signal that could cross back to us. The horizon is one-directional. Information falls in, and the door closes behind it. So physics doesn't hand you a cliffhanger with a resolution waiting off-screen. It hands you a wall and tells you honestly that it doesn't know if there's a room beyond it or if beyond is the wrong word entirely. That silence is where the story's original cold open moment finally gets its explanation. Remember how this all started? That single strange fact, the one that felt like a trick of coincidence, the number that lined up a little too neatly. Back then it was just a hook, a curiosity with no weight behind it. Now look at it again. The mass of everything we can observe, the size of the region we call the universe, and the radius that same mass would carve if it collapsed. Three numbers from three completely different corners of physics, and they meet almost exactly at the boundary of a black hole scaled to hold us. That opening scene wasn't a gimmick. It was the whole argument, compressed into one line, sitting there in plain sight before you had any reason to believe it. And once that moment made sense, one more piece, the very last one, finally fell into place. The rotation period of the observable universe, calculated from the measured vorticity in the cosmic microwave background, comes out to 1.1 trillion years. The light crossing time for a sphere with the current Hubble radius, the time it would take light to traverse the diameter if you could freeze expansion, is 28 billion years. And the Schwarzschild radius for a black hole containing the entire mass energy of the observable universe, 3 × 10^23 solar masses, sits at 13.7 billion light-years. That's not three unrelated numbers. The rotation period divided by 2 pi gives you the dynamical timescale. The light crossing time tells you how information propagates across the volume. And the Schwarzschild radius defines the scale where space-time itself closes off. All three converge within the same order of magnitude. All three derived from independent measurements, all three pointing to the same boundary. You can write it as a dimensionless ratio. The Hubble radius over the Schwarzschild radius for the universe's total mass comes out to about 1, not 10, not 0.1, not 1,000, 1. The cosmological event horizon sits almost exactly where a black hole horizon would sit for an object with the same mass and spin. That's the piece that doesn't go away no matter how you rotate the math. What was left after a number that big wasn't more evidence. It was the question of what any of it means for a person looking up at the night sky. If you're inside, nothing about your morning changes. The coffee still brews. Light still travels in straight lines across the room. You still see galaxies billions of years old, because the light had time to reach you before expansion stretched the space between you, past the point of contact. The horizon doesn't trap you in a cell. It defines the edge of the information you can ever receive. But it does mean the universe you observe is not the universe in full. There's no view from outside, no objective map. Every observer sits at the center of their own bubble, and every bubble ends where the data runs out. You're not seeing reality. You're seeing your past light cone, the stack of every photon that managed to arrive before the space between its origin and your eye expanded faster than light itself. And if the ratio really is 1, if the horizon we see is the horizon that defines us, then the boundary between cosmology and black hole physics isn't a metaphor. It's the same math, written in 2 languages, describing the same edge. Whether you call it an event horizon or a cosmological horizon stops mattering. The structure is the structure. There's one recap left before the real question gets asked one last time. It started with a density coincidence no one could explain. Then the Schwarzschild radius matched the Hubble radius within a factor of 2. Then the cosmic microwave background showed rotation, faint but measurable, with a timescale that locked into the same boundary. And then the math, when you stopped treating black holes and cosmology as separate problems, gave back the same answer from 3 independent angles. If you found this compelling, consider subscribing. There's more like this, and the algorithm only shows you what you tell it you want. Thanks for watching. The real question isn't whether we're trapped inside a black hole, it's whether being trapped was ever the right word. A horizon isn't a wall. It's the place where your story and the rest of the universe's story stop being able to share information. You're not locked in. You're just here, in the only patch of space-time you were ever going to see, watching the light that made it in before the door closed. Here's what makes the horizon different from any barrier you've seen. If you fell toward a black hole, you'd cross the event horizon at a specific moment. But from outside, observers would never see you cross. They'd watch you slow, redshift, and freeze just above the surface, your image fading but never vanishing. That asymmetry is built into the geometry. The horizon exists at different locations, depending on who's measuring. It's observer-dependent, like simultaneity in special relativity. A cosmic horizon around our universe works the same way. Galaxies we see today will, in roughly 100 billion years, cross our cosmic horizon and disappear from view forever. The math describing both horizons is nearly identical. Schwarzschild for black holes, de Sitter for accelerating universes. Both have an entropy proportional to surface area, not volume. Both radiate thermal radiation. Hawking radiation for black holes, Gibbons-Hawking radiation for cosmic horizons. That parallel isn't coincidence. It's why physicists like Susskind argue the holographic principle applies universally. Information about a volume is encoded on its boundary. For a black hole, that's the event horizon. For us, it's the cosmic horizon 46.5 billion light-years away, growing as space expands. The density calculation that started this uses the observable universe's mass, roughly 10^53 kilograms, divided by its volume. That gives 9.9 times 10^-27 kilograms per cubic meter. The Schwarzschild radius for that mass? 13.7 billion light-years, eerily close to the distance light has traveled since the Big Bang. And maybe that's not a prison. Maybe that's just what it means to be somewhere.